This is an induction proof from 2021, paper 1, question 4, and specifically it's a divisibility proof. So just to go through the steps here, the first thing is to give it a name, what we're trying to prove. We'll call it a proposition N, or statement N is the statement we're trying to prove, which is that 2 to the power of 3n minus 1 plus 3 is divisible by 7. Okay, and then we use the analogy of dominoes, knocking dominoes. When you knock dominoes, the important thing is that the first one falls, and also that they're spaced so that each one knocks the one after it. So they are the two conditions for all the dominoes to fall. And we're going to use the same kind of idea here. We're going to knock the first domino, which is the equivalent for us of P1. So what does P1 state? Well, it says that 2 to the power of 3 into 1, put in 1 for n, minus 1 plus 3 is divisible by 7. So we test that out. 3 minus 1 is 2, so that's 2 to the power of 2 is 4. So 4 plus 3 divisible by 7, and it absolutely is. 4 and 3 is 7 divided by 7. Goes in exactly, there's no remainder. So we've knocked, that's the equivalent of knocking the first domino. The next thing we always do is what's called pk. So we take some random domino k in the line of dominoes, and in our case here that means 2 to the power of 3k minus 1 plus 3 is divisible by 7. And we have to assume this. We're not entitled to assume this yet, but we must assume this to see where it leads. That's the logic we're using for the moment. Okay. Now, the next thing is to rewrite it slightly to make an equation. You don't have to do that, but this is a nice way of doing it. So that means what we do is we write it like this, make the same statement in another way. So it's 2 to the power of 3k minus 1 plus 3. What we're saying is if you divide that by 7, you get a whole number. We'll call it a. There's no remainder, basically. So that means that a is an element of z. The whole numbers, the plus, minus, and 0 are the integers. Okay, so we're saying you divide that by 7 and you get a whole number, and that's what this over here is saying, that there's no remainder. Now we rearrange slightly, so we get 2 to the power of 3k minus 1 plus 3 is equal to 7a. So now what you can say is 2 to the power of 3k minus 1 is equal to 7a minus 3. And where does that lead us? So we can actually leave that there for the moment. And the key thing now is this corresponds to any random domino k in the line. Will it fall? So we want to see what does the one next to it fall. So that's the condition for them all to fall, basically. The one next to it, of course, is pk plus 1. So sub in k plus 1 for k everywhere, and you get 2 to the power of 3. So you take that k there and sub in a k plus 1. And there's still a minus 1, don't forget, hanging on the end there, plus 3. And we're saying now that that is basically divisible by 7. But again, we haven't proved this, so this is the question we're asking ourselves: is it divisible by 7? So let's work with this for the moment. So you get 2 to the power of 3k plus multiplied by, well, actually just multiply it out first, plus 3 minus 1 is plus 2 altogether. So 3 by 1 is 3 minus 1 is 2 plus 3. So again, we're checking, is that divisible by 7? That's the key thing we're trying to check now. Now at this stage, in all induction proofs, it comes a time where you try to force in pk into pk plus 1 somehow, and it's no different here. We're going to somehow try and force this into this. Okay, so what we could do up here actually is if we actually draw a line and do another little bit of work back here first to get it ready for pk plus 1. So we might take that and use your rules of indices. And there's a rule that says what you can do is you can take when there's powers like this, 2 to the power of 3k, you can divide it by 2 to the power of 1. Now why is that? There's a rule of indices which says a to the power of p over a to the power of q is equal to a to the power of p minus q. And all I'm doing is using that rule backwards. That's in the tables. So that's what I'm doing right there. So basically is equal to 7a minus 3. And now I have 2 to the power of 3k multiplied across by the 2 is 7a minus 3. So 2 sevens is 14a minus 6. Okay, now this is getting more manageable. We can try and sub it in over here. Just one other step here as well, of course. That can be rewritten as 2 to the power of 3k. Make that a bit easier to read. 2 to the power of 3k by 2 squared. Because again, there's another rule which says if you have a to the power of p multiplied by a to the power of q, it's a to the power of p plus q. And you can go backwards there. And that's what we're doing. We're using that rule backwards. The plus, you can separate them out from the plus to become two numbers like that. So there they are. Plus 3 is divisible, and this is still a big question mark. Okay, finally we can do it. We can now take the 2 to the power of 3k here, and we can sub it in. So we go 14a minus 6 by 2 squared, which is 4, plus 3 divisible by 7. Still question mark, but nearly there. Now we get 4 by 14. 4 fours is, we don't even need that. We can just leave it like that actually, but I'll show you why in a minute. 4 by 14a minus 6 by 4 is minus 24 plus 3 divisible by 7. 4 by 14a minus 24 plus 3 is minus 21 divisible by 7. And now we're there, because if you inspect this closely, you'll see that quite clearly 7 divides into that and that evenly. There's no remainder. You get you basically get 7 into 14 goes 2, so you get 4 by 2 is 8a minus that's 3 times. So you get a perfect number. Again, there's no remainder left over. Basically 7 goes into that perfectly. So basically we've shown that that's true. So this is true. We can actually take off the question mark now and say that's true. So it's true. Okay, so what have we just proved? We've just proved that pk plus 1 is true. Of course, that was all assuming that pk was true in the first place. Assuming that pk is true. So there was a big if, but now we don't have to assume anymore, because there's another part of the jigsaw that fits in now, because don't forget, but P1 is true also. The first domino also fell. So what we're saying now is two things. The first domino always falls. That's true, always true. We did it at the very start back there. We're also saying that if you assume that domino K falls, well, then that definitely knocks domino K plus 1. Now, logically speaking, if you take those two statements together, that's all you need to knock all the dominoes. Or in our case, to prove this is true for every value of n, which is what he asked us to do here. So that's basically it. And so P1 is true. That implies that P2 is true. If you start from there, from P1, and using this statement up here, you can say P2 is true, etc. Which implies that Pn is true for all. That's a nice way of writing, for all values of, that's the way to write it there, an upside down capital A, for all values of n, an element of the natural numbers. And that's the divisibility proof from 2021.